All right, let's go ahead and finish off chapter 3. So now we're actually going to do calculations involving stoichiometry. I wanted to go ahead and talk to you about molar relationships. You have a chemical equation here. This is your combustion of propane. And you should be working on your names. Your 4-carbon C4H10. That's your 4-carbon alkane called propane. But if we're going to use an equation like this in calculations, we need ratios that will allow us to do, wow, I just told you the wrong compound. Uh, I'll just leave it in there so you can make fun of me. It's not propane, it's butane. Whoops. So, yeah, not propane, butane. But is the prefix for 4. All right, so we need ratios uh, that we can use as conversion factors. So, like, for example, let's look at the ratio. Since this is stoichiometry, of course, we're dealing with moles. And so let's look at the ratio of butane to oxygen. So it's like we have 2 moles of butane, 13 moles of oxygen. Okay, what about carbon dioxide to oxygen? So this was comparing 2 species on the same side of the arrow. We can compare species on opposite sides of the arrow. So we can say that 8 moles of carbon dioxide is going to compare to 13 moles of oxygen. Let's see. What if we did, I don't know, water to butane? You can do 10 moles, 10 moles of water to 2 moles of butane. Let's see. What about, if we're going left to right, you could do 13 moles of O2 will yield 8 moles CO2. And so we can just keep looking at these molar ratios. And this is actually going to help us uh, solve uh, solve calculations. So we'll look here. We have a reaction between solid potassium chlorate and red phosphorus. See, it takes place when you strike a match on a matchbox. If we're reacting 52.9 grams of potassium chlorate with excess red phosphorus, and I gave you the formula there, what mass of solid tetraphosphorus decoxide could be produced? So we have to start by writing a balanced chemical equation. There's 2 products, so you have the tetraphosphorus decoxide, and a second product is solid potassium chloride. All right. Wow. So first off, we're being asked for what is the mass? And that gives you one of them. So that's what we're trying to solve for. I know I have to start making my compounds or to write this equation. So I'm going to remind myself. So that's my potassium ion. What about chlorate? That's one of my polyatomics. That's a -1. Chloride. So that's a -1. I'm doing calculations, so I'm also going to need my molar masses of each element. Okay, and then I'm told that my mass of potassium chloride is going to be 52.9 grams. So these are a bunch of knowns that are going to help me solve the problem. So I need my chemical reaction. So of course you see potassium and chloride, it's a +1 and a -1, so that's going to go together 1 and 1. And that's solid. Our red phosphorus, solid. And then that's going to produce our tetraphosphorus dicoxide. So that's O10. That's a solid. And then our other product is solid potassium chloride. You should be getting pretty used to this by now. So I can start taking a look at this, and I can see that I have one potassium, one potassium, one chloride, one chloride. Let's see, on the left, I have 3 oxygens. On the right, I have 10 oxygens. And then on the left, I have 4 phosphorus. And on the right, I have 4 phosphorus. And we got really close, except for the oxygens. Now, automatically, I'm going to start looking at this. I have 3 oxygens on one side, 10 on the other. Now, if I put a 2 in front of the P4O10, that'd give me 20 oxygens, but I can't put 3 into 20. So I'm just going to put 3 in front of the P4O10, give me 30 oxygens. And that means I'm going to put 10 in front of the potassium chlorate and give me 30 oxygens. So let's do that. Okay, so I did that. But now I have the problem of 10 potassium on the left and 1 potassium on the right. 10 chlorines on the left, 1 chlorine on the right. Now, but I do have my 30 oxygens on the left and 30 oxygens on the right. Let's see, I have 4 phosphorus on the left, and but now I have 12 phosphorus on the right. That seems to have really unbalanced us. But we can actually make that up. So I want to try to leave my oxygens alone. So I'm going to say, well, how can I work with phosphorus? And what's really great is having a compound that's only one element. I can put almost any number in front of that to balance out my phosphorus. So what I want to do next is balance my chlorines. I have 10 and 1. I'm going to leave this alone, KClO3, sulfur. So I'm going to put 10 there. That's going to balance my chlorines. And then, of course, I can also do this at the same time, my 4 phosphorus and 12 phosphorus. So if I go ahead and put a 3 there, now I have 12 and 12. And if you count up the atoms on each side, you now have a balanced chemical equation. So here's a little rule to keep in mind. When you're working problems, just because you're given a chemical equation, don't assume it's balanced. If you just start working a problem and your equation is not balanced, you're going to get everything wrong. Always check to make sure it's balanced. If it's not, balance it. That's something that standardized tests will do. They'll give you equations that aren't balanced. Uh, I'm a jackass, so that's something I'll do. I'll give you equations that aren't balanced. So just always make sure you're checking them. Okay, so since we relate species through moles using stoichiometric calculations, we can kind of give ourselves a little map of how we're going to solve this. So this isn't necessarily something you'd have to write into an assignment, but I'm going to end up taking my mass of potassium chlorate, but I have to change that to moles because I want to compare moles to moles. And my chemical equation gives me molar ratios. And then that means I can take those moles to moles of tetraphosphorus decoxide, and then inevitably to the mass of P4O10, which should tell you that if I'm going between mass to moles and moles to mass, I'm going to need molar masses. Okay. So that's why I wrote down the molar masses of all of those elements. So say we have KClO3. That's going to be a potassium plus a chlorine plus 3 oxygens. That's going to be 39.10, 35.45, and 3 times 16. All righty. When I add this up, I'm going to get 122.55 grams per mole. All right. I'm just going to go from potassium chlorate to P4O10, so I only need the molar mass of P4O10. I don't need the others because they're not part of the calculation. It's going to be 4 phosphorus plus and oxygens. It's going to be 4 times 30.97 plus 10 times 16. And that's going to give us a molar mass of 283.88 grams per mole. Okay, so this one I'm going to do in steps, which is perfectly, so I'm going to kind of show you both ways. You can do your calculations in steps, or you can do them as one long calculation. So how many grams of P4O10 am I going to get? Okay, well, let me start with the 52.9 grams KCl, and I need this in moles. Well, how do I do that? I take the mass and I divide by the molar mass, which is going to be 122.55 grams per mole of KClO3. You see that grams divides out, and this is going to end up giving me 0.4317 moles of KClO3. Now I'm going to use the ratio in the periodic table. You notice I have 10 to 3 for my molar ratio. Okay, so that's going to be 0.4317 moles KClO3. And for my chemical equation, that's going to be 10 moles KClO3 to 3 moles of P4O10. And that's good. So you see moles of KClO3 will divide out. This is going to give me 0.1295 moles P4O10. And then I can turn that into a mass, 0.1295 moles P4O10. And then, of course, I'm just going to multiply now by the molar mass, which is going to be 283.88 grams. So if you're going from grams to moles, you divide by the molar mass. If you're going from moles to grams, you multiply by the molar mass. And this will give me a mass 36.8 grams tetraphosphorus decoxide. It's perfectly acceptable to do all of your assignments and all of your work in steps like this. See, moles divides out. Uh, Now, the way I prefer to do it is I just like to make it one big calculation. And so what everything we just did up here in a stepwise process, I'm now going to put into one long grid, just so you can see what that looks like. So again, I'm going to start with the 52.9 grams of potassium chlorate. I know that I have to turn it to moles, so I'm going to divide by its molar mass. And you notice that again, grams and grams divide out. Then I have from my chemical equation. And again, make sure you're taking the time to work through these, because these kinds of calculations we're doing here at the end of chapter 3, they're going to be central to a lot of stuff you're going to be doing over the next several years. So in organic chemistry, biochemistry, analytical chemistry, so on and so forth. These kinds of calculations are going to be very, very central. So you've got all of your labs. So you want to make sure you're getting this stuff down. So remember, it's a 10 to 3 ratio, so 10 moles of KClO3 to 3 moles P4O10. And again, those are the coefficients from our chemical equation. You notice that moles of KClO3 divides out. And now I want to turn mole, and so I have units of moles of P4O10. I want to turn that into grams. So I'm going to multiply 283.88 grams by the molar mass, P4O10 per mole. All right, so then you notice moles of P4O10 divides out, and I'm left with the units of grams of P4O10, which is what I'm trying to calculate. So again, what I'm going to do is I'm going to take 52.9. So this is technically a 1. 52.9 times 3 times 283.88. Then I'm going to divide by 122.55 times 10. So what this would look like, you see in the numerator, 2.9 times 3 times 283.88 over 122.55 times 10. And that's going to end up giving me, again, 36.8 grams of P4O10. So again, I don't care how you do it. You can choose to do it in steps or do it as one long calculation. You don't have to show me this step right here. I'm just showing you how that breaks down. Dots mean multiplication. If it helps, I can do this. But that's how you solve this problem, using the stoichiometry of your equation. So we have another one here. Maybe it's a good time to pause the recording and try to solve this for yourself, but otherwise we're going to move on. So aspirin is synthesized by reacting salicylic acid with acetic anhydride. Now, anhydrides, you're going to have labs that, let me find a good one here. Okay, so well, I'll just give you so common mineral, gypsum. You're going to have these in labs. So this is called a hydrate. So this is calcium sulfate dihydrate. Um, and so one of the ways you work with these in lab is you put them in a dish and you heat them and you bake the water out. So what you can do is you bake these and you can get, for example, the calcium sulfate without the water in there. Now, this is not an anhydride. Uh, this is the anhydrous version of the dihydrate. I just wanted to take a little aside and mention this because this whole thing made me think of it. An anhydride occurs in a chemical reaction where water is completely baked out of your they're not extra molecules on your compound. The water is in your compound in the form of atoms and it's baked out. So that's your anhydride. But is this how you spell it? Yeah. This is the anhydrous form of your gypsum. So the water's been baked out of it. Again, you'll see this in labs pretty soon. So I just wanted to take a little aside and mention it. But so it's like if you wanted to find your molar mass of your hydrate, you would find the molar mass of your calcium sulfate plus the molar mass of two waters. So make sure you're looking at that when you come across the lab where you see that. This is how you start working with your masses and how that all works. But yeah, your anhydrous compounds are not anhydrides. It's a similar concept, but they're not the exact same thing. But again, it kind of told me it's like, oh, here's a definition you might not know. So let's cover it before you see it in lab and you're going, what is that? Okay, so back to this. So your equation for the production of aspirin is right here. Now this is balanced, but make sure you double check it. Always make sure you double check. But we're just going to do a calculation here. On an exam, you can fully expect that I would also ask you to name that. I'm not going to ask you to name these organic compounds you haven't seen before, but this one at the end, you've seen this one. And this one is a hydrogen on an acetate ion. That's acetic acid. So if I ever ask you to name something, it's something you should know. So keep that in mind. So let's see, what mass of acetic anhydride, and that's going to be at your acetic anhydride. This one is your salicylic acid. So what mass of acetic anhydride is needed to completely consume 1.0 times 10 to the second grams of salicylic acid? And then B, what is the maximum mass of aspirin, the theoretical yield, that could be produced in this reaction? I want you to start to wrap your mind around this concept of theoretical yield because you're going to be talking about limiting reagents, you're going to be talking about percent yields. Theoretical yield is the smallest amount of product that can be made in the given reaction. So usually that means that one of your reactants is completely used up and then the reaction stops. And so you need to know what that minimum yield is so that you can, A, talk about what the limiting reagent is, and then B, what your theoretical yield is, because you can't produce any more product than you have of reactants. And when one runs out, you're done. So your theoretical yield is going to be produced by your limiting reagent. And that theoretical yield is what you should be yielding in a reaction if it goes to 100%, which they don't often do. So start wrapping your mind around that concept. Okay, so for part A, We want the mass of acetic anhydride. Okay, what's some things that we know? The mass of salicylic acid that I'm using If you don't want to write the scientific notation, you can just write 100 grams. That's fine. Let's see. Put the decimal point in there so it stays at 3 significant figures. We can guess, since we're going to be doing stoichiometric calculations, we're going to need molar masses. And then oxygen. We round it to 16. So here's some knowns that'll help us solve this. So I'm comparing acetic acid, let's see, acetic anhydride to salicylic acid. So I'm going to need the masses of each of the molar masses of each of those. So my acetic anhydride, that's going to be 4 carbons plus 6 hydrogens plus 3 oxygens. It's going to be 4 times 12.01 plus 6 times 1.01 plus 3 times 16. That is going to yield 102.09 grams per mole. I'm also going to need salicylic acid, so C7 H6O3, that's going to be 7 carbons plus 6 hydrogens plus 3 oxygens. Okay, so 7 times 12.01 plus 6 times 1.01 plus 3 times 16. That is going to yield 138.12 grams per mole. And now I just want to go from my 100 grams of salicylic acid to my acetic anhydride. Now I told you you can break this apart into calculations or do it as one big one. I like doing them as one big one, so that's what you're going to see. Okay, so let's see. So we start with our 100 grams of my salicylic acid. All right. Now in stoichiometric calculations, I need to get the moles, so I'm going to divide by the molar mass. Of salicylic acid. Then I go back up to my equation and I see that they have a 1-to-1 ratio. I know it seems tedious, but I want to see you write this step down because technically you wouldn't have to mathematically because it's just 1/1. But I want to make sure that you understand the molar ratios from the chemical equations. So just get in the habit of writing that step down. And then I want to go to grams of acetic anhydride. And so I need to multiply by its molar mass. All right. So then you notice that grams divides out, moles of salicylic acid divides out moles of salicylic acid, moles of acetic anhydride divides out moles. And I'm left with my grams, my mass of acetic anhydride that I'm looking for. So I multiply this all up, and this is going to give me 73.9 grams of acetic anhydride. Okay, so now part B. What does it say? What is the maximum mass of aspirin that could be produced in this reaction? Now, we don't have to go all the way through and find out what the limiting reactant is in this case. First off, we haven't talked about that, but second off, because of part A, it says what mass of acetic anhydride is needed to completely consume the salicylic acid. Okay, so I know I have 100 grams of salicylic acid. I'm going to figure out how much acetic anhydride I need to completely neutralize that, and or break it down or react with it, however you want to say it. But the reason I don't have to find limiting reagent is because I've measured out a specific amount of the acetic anhydride, and when they react, they're going to completely consume each other. So there's no reactant in excess. So I can use the numbers from either one of them. I could use the 100 grams of salicylic acid or the 73.9 grams of acetic anhydride to do this next calculation, because the 73.9 grams molar wise will completely cancel out the 100 grams of salicylic acid. I chose to use the 73.9. So this calculation is going to be, let me move this. Of course, what I'm looking for here is mass of aspirin. We want to name what it is we're looking for, since now we're being asked for something different. Okay. And so I'm going to use the C4H6O3. And now I need to do a mole-to-mole comparison. So I need to get this into moles. So I'm going to divide by acetic anhydride's molar mass. And so then for my chemical equation, I have 1 mole of my acetic anhydride to one, it produces 1 mole of aspirin. And then I want to get aspirin into grams, so I'm going to multiply by its molar mass, which of course, I forgot to do that first. So, okay, we don't have one of our molar masses. So let's figure out what that is. C9H8O4. It's going to be 9 carbons plus 8 hydrogens plus 4 oxygens. 9 is 12.01 plus 8 is 1.01 plus 4 times 16. This is going to give me 180.16 grams per mole for aspirin, so that's what I need here. Okay, so my grams of acetic anhydride cancels out, moles of acetic cancels out, and then moles of aspirin cancels out, and I'm left with grams of aspirin. And when I multiply this all up and divide by the bottom, this is going to give me 130 grams of aspirin. Okay. Now we talked about the fact there's no limiting reagent here because the acetic anhydride was specifically measured out. And so molar wise, they're going to cancel each other out. So now you can do your calculations the way we just did them. If you wanted to do shorter calculations, you could have done this. You could have said, well, 100 grams of salicylic acid. No, that's, yeah, salicylic acid. Okay. What is this in moles? So we could have just calculated this. And the amount of acetic anhydride that we had to measure out, the 73.9 grams, is also going to give us 0.724 moles. So I could have done this first, and then every calculation from there, let's see, every calculation from there, I could have cut out this first part and just started with the moles and gone to grams. But however you want to go about it is fine. I don't know. I usually just go straight into calculations. Sometimes I'll do pre-calculations to make things shorter. It doesn't really bother me. It's really however you want to think about it. But make sure you're getting the hang of this. And we're going to go into talking about limiting reagent. So limiting reagent or limiting reactant, of course, is exactly what it sounds like. You're going to have your reactants in a reaction, and you're going to have different amounts of them. And one or more of them will get used up before the end of the reaction. Once a reactant is used up, the reaction stops. You can't go any further. And so you'll have one that's completely used, which is your limiting, and others that are in excess. Uh, and so what that means is, like, let's see here, you have hydrogen. I'll pretend these are hydrogen molecules. Yeah, but however it is, however you want to imagine it, we have hydrogens and oxygens. These are going to produce water, but you know water is H2O. Let's see, I have 8 hydrogens and 3 oxygens. That means I can only produce 3 waters, which is going to be 6 hydrogens, and that means that I have 2 hydrogens left over. So in this case, oxygen was the limiting reactant, and I have hydrogen in excess. So if I'm trying to figure out how much water is produced, that's going to be dictated by the amount of oxygen I have, not the amount of hydrogen. This is the whole idea behind a limiting reactant. I think it's best just to start in with some problem exercises and look at it. So here we have a reaction. Oh, I hope you can name every single one of these. So we have calcium phosphate plus sulfuric acid yields calcium sulfate plus phosphoric acid. This is, of course, another double replacement that we talked about last time. It's a little harder to see, but notice how the sulfate and phosphate switch places. And this is a specific kind, again, called a precipitation reaction because we get a solid as a product. So we say what masses of calcium sulfate and phosphoric acid can be produced from the reaction of 1.0 kilograms of calcium phosphate with 1.0 kilograms of concentrated sulfuric acid. Now here's a little clue. You notice how I have an exact amount of each reactant? That should automatically trigger in your head, this is probably going to be a limiting reactant problem. A lot of problems you'll see, like it would say 1 kilogram of calcium and then excess sulfuric acid. If it says excess, well, you already know it's not limiting reactant because you already know that the one that's not in excess is the limiting reactant. But here, since we have an exact amount of each reactant, it's going to be limiting. We need to figure out which one is the limiting reactant. Now, The first thing we do is we go, oh, that's not balanced. Okay, so let's balance it. And I'm going to go ahead and show you what it is, but work through this and make sure you're getting it. You're going to have 3 of the sulfuric acids. You're going to have 3 of the calcium sulfates. And I'm going to need 2 of the phosphoric acids. Okay, now it's balanced. What is it asking for? Mass calcium sulfate, mass of phosphoric acid. Okay, and so it's asking for theoretical yields of these 2 compounds. And we will only get as much of these compounds as the limiting reactant can give us. So we're looking for that smallest number. Now, I could take my exact mass of each one of these reactants and calculate through to the masses of calcium sulfate and phosphoric acid. And then whichever the smaller numbers were, those would be my theoretical yields. So we can always do that. We can also compare reactants to figure out which one is limiting. Okay, so some things that I'm going to need. Put this up. All right, so calcium, 40.08 grams per mole. That's phosphate. Okay, so sulfur, 32.07 grams per mole. Hydrogen, 1.01 grams per mole. Phosphorus, 30.97 grams per mole. And oxygen is 16 grams per mole. So again, when you're writing down your list of knowns, something that's always going to go in there are things that you should know that are not listed in the exercise. Those will always go in there. Okay. So since I'm going to have to do some calculations here involving all the species in the reaction, I'm going to end up needing molar masses of those species. Calcium phosphate, at least 3 calciums, plus 2 phosphorus, plus 8 oxygens. It's 3 times 40.08, plus 2 times 30.97, plus 8 times 16. This is going to give us 310.18 grams per mole. All right, so sulfuric acid, hydrogen, plus the sulfur, plus 4 oxygens, 2 times 1.01, plus 32.07 for the sulfur, plus 4 times 16 for the oxygen. This is going to yield 98.08 grams per mole. You should be getting pretty used to this. So when we do this exact same process for calcium sulfate, we're going to get 136.14 grams per mole. And for phosphoric acid, we are going to get 98 grams per mole. Okay, so now we have our molar masses of all of our species. Now I want to find out what the limiting reagent is. So what I'm going to do is I'm going to do a calculation to compare my reactants. So if I have 1 kilogram of calcium phosphate and I calculate it all the way through to a mass of sulfuric acid, what is that mass? All right. So we know 1 kilogram is 1,000 grams. Calcium phosphate. Oh, let's see. Now I need to turn this into moles. I need to divide by the molar mass of calcium phosphate. Grams is going to divide out. Okay, so then I need my molar ratio. I look at my chemical equation. There's 1 calcium phosphate, 3 sulfuric acids. So that's going to be 1 mole. Oopsies. Calcium phosphate with 3 moles. Sulfuric acid. And of course, moles of calcium phosphate divides out. And then I need grams of sulfuric acid. So I'm going to multiply by its molar mass. And moles of sulfuric acid divides out. And when I calculate this, this is going to give me 948.6 grams of sulfuric acid, which is also 0.9486 kilograms of sulfuric acid. So if I use the full kilogram of calcium phosphate, that's only going to use up 0.9 kilograms of sulfuric acid, but I'm told that I have a full kilogram of it. So that tells me that I will have sulfuric acid in excess. I will have sulfuric acid left over, which means that my calcium phosphate is limiting. So now I can do all my calculations with that knowledge. So let's calculate the amount of calcium sulfate first. So how much am I going to get? Okay, so I'm going to do everything from this, calculate using the limiting reactant, because again, once it's gone, the reaction stops and I have what I have. Okay, so let's see, molar mass of calcium phosphate. All right, that's going to divide out grams of calcium phosphate. And my molar ratio from the chemical equation, again, is 1 calcium phosphate to 3 calcium sulfates. Again, you're using your coefficients here, and they're in moles. All righty. And so moles of calcium phosphate divides out. And then I need grams of calcium phosphate, so I need to multiply by its molar mass. 136.14 grams calcium sulfate per mole. And moles divides out. And when I multiply this all out, I'm going to get 1316.7 grams of calcium sulfate, or 1.317 kilograms calcium sulfate. I would accept either answer. Now let's do this again for the phosphoric acid, because we also need to know how much of that we get. All right, same calculation. Doing limiting reagent problems, this calculation is going to get very old very fast, but you're going to really master it. And then you'll do limiting reactant again in lab. You'll do it in organic chemistry, and so on and so forth. You'll do it in biochemistry. You'll do it in analytical chemistry. And so just hold on for the ride. And then you'll do it again once you're in medical school. 310.18 grams per mole calcium phosphate. Grams cancels grams. From the chemical equation, 1 mole of calcium phosphate gives 2 moles of phosphoric acid. Moles of calcium phosphate cancel out. And then I need a mass, so 98 grams of phosphoric acid per mole. And moles divides out. And when I calculate this is going to be 631.9 grams phosphoric acid, or 0.6319 grams, oh, not grams, kilograms of phosphoric acid. All right, so now you've solved this problem. And so, like I said, I compared the reactants first to get it to find out which one was limiting that way. That's one way to do it. I don't necessarily have to. I could just take, for example, I could just take the calcium phosphate and calculate both of these. And then I could take the sulfuric acid and calculate both of these. And my smaller numbers would be the ones that I take, because you would see that the calculation showed that the numbers for calcium phosphate were smaller, meaning calcium phosphate is limiting, meaning that those masses are the extent of what you could get. So you would just neglect the numbers from the sulfuric acid calculations. We're going to do the next example. We're going to do the calculation in that manner, so you'll see what I'm talking about. Okay, so acrylonitrile is the starting material for many synthetic carpets and fabrics. Is produced by the following reaction. Always double check it, but you're in luck. This is balanced. So if I have 15 grams of C3H6, 10 grams of O2, and 5 grams of ammonia, what mass of acrylonitrile can be produced assuming 100% yield? 100% yield is percent. So it is exactly what it sounds like, a percent yield. It'll make more sense in our final calculations for the chapter, but right now we're just assuming that it goes all the way to 100% completion. Now, don't try to name C3H6 just now. I mean, we've worked on the alkanes, but this is propene. And so you'll find out in organic chemistry, you have alkanes, alkenes, and alkynes, the E and E ending. indicates a double bond, whereas your prefix indicates 3 carbons. So I would not ask you to name that right now. You should know your alkanes, but beyond that, you'll pick that up as you go along. So what this is asking for, oopsies, mass of acrylonitrile. All right, well, I'm going to have to do a stoichiometric calculation, so I am going to need molar masses from the periodic table. Yeah, if you forgot where I was getting these are your masses from the periodic table. And for E, we round oxygen to 16. But we also want to make sure we realize that we have 15.0 grams of propene, 10 grams of O2, 5 grams of NH3. I mean, if you're really asking yourself, how do I know what to put in that knowns, the list of known quantities for a homework, you don't have to perfectly predict what I do or perfectly match what I do. You need to put forth an effort and you need to make a list of things that you should know that will help you solve the problem. Now, like here, your molar masses of your elements always are going to need to go in there because they're not part of the exercise, but you should know them. You should be able to find them. And so you're definitely going to want to write those down, but make a list that's going to help you solve the problem. Okay, so I know that I'm doing stoichiometric calculations, which tells me I'm going to start by calculating my molar masses. C3H6, that's going to be 3 carbons plus 6 hydrogen with 3 times 12.01 plus 6 times 1.01, which is going to be 42.08 grams per mole. All right, what else do we have? We have ammonia, 1 nitrogen plus 3 hydrogens. That's going to be 14.01 plus 3 times 1.01. That's going to be 17.03 grams per mole. And again, by now, you should be getting used to this O2. That's going to be 2 oxygens, so 32.00 grams per mole. And my acrylonitrile C3H3N. I add all that up, and I'm going to get 53.06 grams per mole. Okay. So then the question is, how much acrylonitrile can I get from this reaction? Well, I'm not, look at the chemical reaction. I'm not going to compare, well, I mean, I could, but I chose not to compare reactants again because I'd have to take several ratios and try to figure out what the limiting reaction is. I could take the masses of each reactant, calculate the moles of each reactant, and then I could divide those moles by the coefficients, and whatever the smallest number there is, that's your limiting reactant. Because again, that tells you the moles that you get. That's going to tell you how many reaction cycles you'll get out of that mass of your reactant. And if you divide by when you divide by your coefficients, it's telling you how many reaction cycles you get. So whatever the smallest number is, that's going to be the number of reaction cycles you get, meaning that the other two larger numbers are going to be in excess. You could do it that way. What I chose to do is I'm just going to say, well, I'm going to calculate acrylonitrile just using each individual reactant. I've always found that to be straightforward and simple. It might take a few steps longer, but I like the way this works. So I'm going to start with the propene. All right, well, I have 15 grams of it. And the molar mass of propene is 42.08 grams per mole of propene. Again, I'm going to moles because that's what that's how the coefficients in the reaction compare. I go to the chemical equation and I have 2 moles C3H6 to 2 moles of acrylonitrile. And again, I know you say, well, that's a 2 to 2 ratio. Couldn't I just leave that step out? Technically, yes. But for right now, I want you writing it in because I want to make sure you're doing the proper ratios. And now that I have moles, so let's see, grams cancels out, moles of propene cancels out. I need to take moles of acrylonitrile to grams. So I'm going to use its molar mass, 3.06 grams of acrylonitrile per mole. And of course, moles of acrylonitrile cancels. I'll do 15 times 2 times 53.06 divided by 42.08 times 2. And this is going to end up giving me 18.9 grams C3H3N. All right. That might be the amount of acrylonitrile I get, but I don't know yet. Let's do the calculation again for ammonia. All right. 5 grams of ammonia. You should be seeing by now that you're going to get very good at this type of calculation. The molar mass of ammonia is 17.03 grams per mole. Now I have everything in moles of ammonia. Grams is gone. From the chemical equation, it's 2 moles of ammonia to 2 moles of acrylonitrile. And now that I have moles of acrylonitrile, I need it in grams. So moles of acrylonitrile cancels. This is going to give me 15.6 grams of acrylonitrile. Well, whatever happens, I know because of ammonia, I absolutely cannot get 18.9 grams because ammonia will run out when I reach 15.6 grams. All right, well, let's see what oxygen does. Okay, so I had 10 grams of oxygen. Turn it into moles. 32 grams per mole of oxygen. The mole to mole ratio, because now grams is gone. Mole to mole ratio. This time we have 3 moles of O2 to 2 moles acrylonitrile. Again, coefficients from the chemical reaction. And now that I have those moles of acrylonitrile, I need them in grams. Moles is gone. And this is going to leave me with 11.1 grams of acrylonitrile. That That's my smallest number. So that means that oxygen is my limiting reactant. And that means oxygen is going to run out before either the ammonia or the propene does. So I'll just have excess of ammonia and propene sitting around. But the oxygen will be completely used. And once it's used up, I have 11.1 grams of acrylonitrile, which is the maximum amount I could get. Or my theoretical yield. Okay. So you see here how I can just take each reactant, take it through to completion, and whatever the smallest number is my answer. All right. So your last important calculation you're going to need is your percent yield. This is going to be a quantitative analysis of the experiment you do. So you're going to have a theoretical yield, but you're going to do your experiment, then you're going to weigh, you're going to measure your products, and that'll give you an actual yield. And so, so then you say, well, how much, what is the percentage that I got? Yield? Uh, Yield. There we go. Did I spell it? Yeah. Okay. But this is going to tell you like well, how well did the reaction actually do? And I'll tell you, those of you who are perfectionists who want your 98, 99% yields, get over that because once you get to organic chemistry, the yields go way down. So just to prevent yourself from having a nervous breakdown, just know that the yields are going to be low in organic chemistry. And it's not necessarily you. Okay, so let's look at this. Here we have a reaction. Solid phosphorus mixes with solid fluorine to produce phosphorus trifluoride. Again, make sure you can name things. What mass of fluorine is needed to produce 120 grams of phosphorus trifluoride if the reaction only has a 78.1% yield? Okay, so we're being asked for that. Things that I know. 120 grams. I'm going to write it that way so it makes sense to me. I know fluorine from the periodic table is 19.0 grams per mole. Phosphorus is 30.97 per mole. Okay, so those are my knowns. I check and my equation is not balanced. So you can go through the steps to balance it, but once you get there, it's going to be phosphorus plus 6 fluorines. It's going to yield 4 phosphorus trifluorides. And of course, that's phosphorus trifluoride. I'm naming it like a covalent compound because phosphorus and fluorine are both nonmetals. And so when two nonmetals combine, covalent compound. Okay, so let's start setting myself up with some numbers I know I'm going to need. F2 is 2 fluorines. It's going to be 2 times 19. Or 38 grams per mole. Let's see, phosphorus trifluoride. There's going to be a phosphorus plus 3 fluorines. So 30.97 plus 3 times 19. That's going to equal 87.97 grams per mole. Now, I have to use that percent yield to say, well, what is my theoretical yield? Because my theoretical yield is what I would get if this goes to 100%. That theoretical yield is what I'm going to use to calculate fluorine. Because to calculate how much you need of a reactant, you need to assume 100%. Because if I only did my calculation from the 120 grams and got a mass of fluorine from that, well, then the reaction would only produce 78% of the 78%, so it produced less. So I need to know what those numbers are at 100% so that I make sure that I'm getting my maximum yield. Okay, so take that hodgepodge I just said and find a way to make it make sense to you. I need to know what the yield would, what my numbers are at 100%. I need to know what my numbers are to maximum yield. It doesn't matter what my numbers are. I'm only going to get 78.1%, but I want to maximize the yield. So I'm going to start with my equation. Percent yield is going to be actual over theoretical times 100. Okay. So I'm going to divide through by 100. So percent yield over 100 is going to be actual over theoretical. Okay. So I'm going to multiply through by theoretical. Going to equal actual. And then my theoretical yield that is going to be actual divided by this little fraction. Now you remember when I have a fraction in the denominator, I flip and multiply. So my theoretical yield is going to be 100 times the actual yield divided by my percent yield. All right. So now this is an equation I can plug numbers into. Theoretical, 100. My actual yield is the 120 over the 78.1, which is my percent yield. This will give me 153.6 grams of phosphorus trifluoride. So if I got 100% yield, this is what I would have gotten. This is a number that I need to use to then say, well, what mass of fluorine do I need to get this 120 grams? Again, that's why I'm trying to maximize it. If I just start with the 120 grams and I calculate fluorine from there, and that's all I put in the reaction, I'm only going to get 78.1% of that 120. I'm not actually going to get the 120. So I need to calculate it from 100% yield. All right, so this means I'm going to do my 153.6 grams of phosphorus trifluoride that I just calculated. And so then I want moles. So 87.97 grams per mole of phosphorus trifluoride. Gram cancels. Okay, my molar ratio. Let's look here. My molar ratio of phosphorus trifluoride to fluorine is 4 to 6. So I'm going to need 4 moles of phosphorus trifluoride to 6 moles of my fluorine. And again, I put it in this order because I need moles of phosphorus trifluoride to divide out. And I'm going to use the molar mass of fluorine to get grams. And going from moles to grams, I'm going to multiply by the molar mass because you're seeing moles of fluorine now cancels out. So I'm going to multiply this out, and I see that I'm going to need 99.52 grams of fluorine to yield the 120 grams of phosphorus trifluoride. So you're going to end up practicing quite a bit. I'll have another assignment out tomorrow morning. And so this is the end of the material that you'll need for the exam that I'm going to put up on Friday. And I know there's a holiday coming up, so I'll explain how that's all going to work. But so this is going to end chapter 3. And on Thursday, we are going to start chapter 4. All righty. Thank you.